So quantifying heat and work. So heat is a transfer of thermal energy between the system and the surroundings that's caused by a difference in temperature. Temperature measures the average thermal energy within a sample. So temperature and heat are different. Heat involves a transfer of energy. Temperature is just how hot is the thing right now. So heat flows from something with a high temperature to a low temperature until both objects are the same temperature. Because if you put an ice cube in a cup of coffee, what happens to the temperature of the coffee? It gets down. It goes down, right? Does it do that every time? Every single time. Because heat is flowing from the hot coffee into the cold ice cube. You never have a situation where the ice cube gets colder and the coffee gets hotter, right? Doesn't happen. The transfer of energy through heat will occur until the things come to the same temperature. So I've got my rock star here. There's a little bit of ice left in it. This has been in contact with it's been a mixture here for over 2 hours now. Yeah, make this thing last a long time. The temperature of the ice and the temperature of the liquid around it are the same temperature. Because if they weren't, heat would flow until they were. And that's what happens. So that's called thermal equilibrium. The two things are at the same temperature. There's no additional net transfer of heat.
In thermal equilibrium, are both substances constantly exchanging energy back and forth like a chemical equilibrium?
That's an excellent question. And notice this, it says no net transfer of heat. So yes, on a small scale, there's heat being transferred from one thing to another and back again. But overall, there's no transfer. Yeah. So if a system absorbs heat, its temperature is going to go up. And we can call that change delta T. The increase in the temperature is going to be proportional to the amount of heat that's absorbed. If it gets more heat, the temperature is going to go up higher. If it gets less heat, it's going to go up less. So it's proportional. So there's a proportionality constant. So we could say that the change in temperature is proportional to the amount of heat. And so to make that an equal sign, we need a constant here. So Q is equal to a constant times the change in temperature. That constant is called the heat capacity. And it's going to have units of energy per degree in temperature. So joules per degree Celsius or joules per Kelvin. So heat capacity, symbol C, and that is not as universal as most of these other things. Some books will call it S or something. The heat capacity is the heat required to change the temperature of the system by 1 degree. Well, the larger the heat capacity of the object, the smaller the temperature rise will be. But the heat capacity of an object depends on how big the object is, right? And we usually measure that by mass. So heat capacity is an extensive property. It depends on how much stuff there is. We would like this to be an intrinsic property, so we don't have to be factoring in the mass all the time. So the specific heat capacity, this is what we use almost exclusively. The specific heat capacity, so C sub S, is the intrinsic capacity of a substance to absorb heat. So the heat capacity depends on the mass, and it also depends on the type of material. some things heat up much more easily than others. So specific heat capacity, the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So this is going to have units of joules per gram degrees Celsius. That's how it's easier to put them into a computer. Joules divided by grams times degrees Celsius. That's the same thing. Sometimes we talk about the molar heat capacity, and so then that's the amount of heat needed to raise the temperature of 1 mole of the substance by 1 degree Celsius. And so the units there would be joules per mole times degrees Celsius. These are intrinsic properties. They do not depend on how much stuff there is. Because if you think about maybe making spaghetti, so if you're cooking spaghetti for yourself, you probably just need a couple cups of water, and you stick it on the stove, and you turn the burner on, and it boils fairly quickly, right? If you're trying to make spaghetti for the football team, and you need 2 giant pots of water, actually let's say 2, just the one really bigger than would fit in your kitchen, pot of water, and you stick that on your stove at home, and you turn it up full blast. And you wait, and you wait, and you wait. And it takes longer. The water was the same temperature to start with. I'm just trying to boil it. Why does it take longer? Because there's more water, right? On a commercial stove in the cafeteria kitchen, 45 minutes to boil a pot of water. Personal experience. So this is the equation that relates all of this stuff. And that's got all these, all this information around it, so I'm just going to write it. Q equals MC delta T. So sometimes it's easier to think of that as Q equals MCAT, because that delta kind of looks like a capital A, right? So if that helps you remember it, Q equals MCAT, Q equals MC delta T. So Q is the heat in joules, M is the mass in grams, C sub S is the specific heat capacity. Should put an S there. We get really sloppy about that. Specific heat capacity, joules per gram degree Celsius, and delta T is the temperature change. So if we look at the units here, the mass would be in grams, the specific heat capacity is in joules per gram times degrees Celsius, and the temperature is in degrees Celsius. The grams cancel, and the degrees Celsius cancel, and Q is in joules. Specific heat capacity is going to be different for different substances, and you don't memorize these. You look them up in a table, and here's a table that's probably going to be good enough for all of your homework assignments. This is not everything, but it's some interesting, useful things, common things. So lead, gold, silver, these different metals, their specific heat capacities are small. And then we have ethanol and water. Water's specific heat capacity is 4.18 joules per gram degree Celsius. Much, much higher than the metals. And then there's some other materials like glass, granite, and sand, and these also have quite low specific heat capacities. So a low specific heat capacity means that you're going to get, when you put in a certain amount of energy, you're going to get a bigger temperature change than for something that has a high specific heat capacity. It's hard to change the temperature of water, which is a good thing and a bad thing. Water can absorb a lot of heat energy without changing its temperature very much because it has a very high specific heat capacity, like about 4 times most other things or more. So water moderates temperature on our planet, and it does this, it's a lot due to the water. So if we think about an area like San Francisco is on a peninsula, and it's surrounded by water, the San Francisco Bay and the ocean on the other side, and there's water all over the place. And so when the sun beats down in the middle of the summer, a lot of the energy from the sun is absorbed by the water. The water temperature goes up a little bit. And then when the sun goes down, the air is cooler and the water releases its energy back into the air and it moderates the temperature. So in San Francisco, the high might be 68 degrees Fahrenheit in August. And here in Fresno, we'd think it was a fairly nice day if it was only 100 degrees, right? Because here in the Central Valley, there aren't any large bodies of water. I mean, there's some ditches and some canals, there's irrigation, but that's not nearly as significant as a large body of water like the ocean. Water is commonly used as a coolant because it can absorb a lot of heat and remove it, say from your car engine, and keep the car engine from overheating. So when the internal combustion engine runs, you have these combustion reactions that cause the pistons to move, but there's heat energy released by that reaction, and there's also heat from friction, and so the car engine can get very hot. If it gets too hot, it's going to be damaged. And so the car has a coolant system that runs water throughout the engine, and the water absorbs the heat. But the water only changes temperature a little bit because it has a high specific heat capacity. And then it takes it over to the radiator where you've got air blowing through, and the air takes the heat from the water, and then the water goes off and cools some more things. Any questions?
Slide that you made the 100 degrees Fahrenheit.
I did. Thank you. Okay, so I fixed the typo. 100 degrees Fahrenheit. You don't want to misrepresent Fresno. Okay, so here's a problem with a whole bunch of words. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. So all of that being said, would there be an easier way to figure out if this is gold? We could measure the density a lot easier. She's already got the mass. You could put it in a graduated cylinder with water and measure the volume by displacement, but I don't know. Maybe there's, I don't know. We just have to solve the problem anyway, even if we think it's stupid. Okay, so we've got numbers. Again, pull out the numbers. So we've got 4.7 grams, and we've got 57.2 joules, and we have 25 degrees Celsius, and we have 57 degrees Celsius. And it's talking about specific heat capacity, and so we should be thinking of this equation, Q equals mc delta T. Well, 4.7 grams is the mass, right? It says mass of. So I'm going to call that M. 57.2 joules, what's that? Heat. This is a nice first problem. Joules of heat, it tells us that, so heat is Q. And then I've got two temperatures. What I need is delta T, right? Delta T is the final temperature minus the initial temperature. Well, what's the initial temperature? 25. It says from 25 to 57. So 25 is the initial, and 57 is the final. So delta T is 57 degrees Celsius minus 25 degrees Celsius. Which is what, 32? So I have M, I have Q, I have delta T. The question is asking me to find C. So I need to rearrange this equation. So I'm going to divide this side by M, and I'm going to divide by delta T. So those cancel out. And then I have to do the same thing to the other side, divide by M, and divide by delta T. So the specific heat capacity is equal to Q divided by N times delta T. So Q is 57.2 joules. And then I'm going to divide it by the mass, which is 4.7 grams. And the change in temperature is 32 degrees Celsius. And this is another situation where we've got two numbers in the denominator, so we have to make sure that we get it correct. If you're going to, if you really want to multiply these, then you have to put parentheses around the denominator. I do 57.2 divided by 4.7 divided by 32. And we'd have two significant figures on this, 0.38. And then none of those units cancel out. So they're all just sitting over here. Joules divided by grams times degrees Celsius. That's okay, because those are the units of specific heat capacity. So there's the specific heat capacity. Is that consistent with this being gold? No, but we have to look this up to find out. So we have to go back to the table, and gold has a specific heat capacity of 0.128, and the one we've got is 0.38, which looks a lot more like copper, right? Now, if this was gold, would I get exactly 0.128? No, but it would be close. Right? I might get 0.125 or even 0.13 or something close, right? But 0.38 to 0.128, this can't be gold. Does it prove that it's copper? No, because it could be a mixture of all kinds of other things as well.
So if it was close to the specific heat capacity of gold, it still wouldn't prove it was gold?
It would not prove that it was gold. And that's why the question says, is the value consistent with the rock being gold? So if I got 0.13, that would be consistent with the rock being gold. It'd be highly suggestive, but not proof. Yeah, you'd have to do some more tests. Any other questions?
Would the density prove that?
The density would help. But again, you can make a combination of other substances that would have the same density as gold. Not necessarily cheap or easy to do. Usually when it's soft, but lead is soft too. Gold has a really high density, and so when you see movies and they've got like this sack of gold coins and they're running down the street, no way. They could barely lift it, maybe. They definitely can't run with it. So you pick up something that's solid gold, and it seems very heavy for its weight. You can imagine taking a cardboard box and painting it beautifully to look like a brick, right? But when you pick it up, you know immediately that's not a brick because it's way too light for its size. So if you had the specific heat capacity and the density both match up, that would be pretty good. .38 joules per gram degree Celsius, and no. So this capital Joule, I really like this font, except the capital J. Yeah, kind of looks like something else. I don't know. Let's do another one. We'll just do this one example, and then we'll just quit in the middle of this section because we need to do our experiment. A 55-gram aluminum block initially at 27.5 degrees Celsius absorbs 725 joules of heat. What's the final temperature of the aluminum? Well, we write down the numbers. 55.0 grams, 27.5 degrees Celsius, 725 joules. Well, 55 grams, gram is a unit of mass. This is a temperature, and it says it's initially at 27.5, so this must be initial temperature. And it says it absorbs this much heat, so Q is equal to that. And so the equation I'm going to use is Q equals mc delta T. But I'm trying to find the final temperature. T final isn't in that equation, right? But I know that delta T is the final temperature minus the initial temperature. I have the initial temperature, so if I found delta T, then I could find out what the final temperature is. You can put TF minus TI into this equation, but then there's distributing involved, and I think it's better not to, unless you're really good with algebra. So what I'm going to do is I'm going to solve for delta T. So divide by M and C. Divide by M and C. The M's cancel out. The C's cancel out. So delta T equals Q divided by mass times specific heat capacity. So I've got Q, I've got M, but I don't have a specific heat capacity. I have to go look it up. It says it's aluminum. So I go back to my table. Aluminum, 0.903. I'll just put that down here. C sub S equals 0.903 joules per gram degrees Celsius. So in the numerator, I have the mass, 55 grams. And in the denominator, no, that's not the mass. Q is in the numerator. Q, 725 joules. The mass is down here. And the specific heat capacity. $725 divided by 55 divided by 0.903. I've got 3 significant figures. So 14.597 degrees Celsius. That's the change in the temperature. Looking at this relationship over here, the final temperature is equal to the change in temperature plus the initial temperature. So 14.597 plus the initial 27.5. .097, 42.1 degrees Celsius. Is that reasonable? It moved in the right direction. And that's what was initially freaking me out when I saw the 14.5. It's like, wait a minute, the temperature's supposed to go up. And then I realized, oh, duh. So that was the change in temperature. So it absorbed heat. The temperature has to go up from 27.5. Any questions? $42.1.